Hi, everyone. Thank you to this edition of Reline Live. Today, I get to welcome the Dons instead of just one Don, who's been joining me quite frequently. This time, we also have Don McGriff. Thanks, Don McGriff, for joining us this time.
Glad to join you.
Yeah, it's good. And then we also have our regular co-host, Don LeBlanc, is here to join us, and we are going to be talking about inlet geometry. This is very new to me. This is much more of an engineer-focused conversation. And with that, I am going to let these guys kick it off. Oh, sorry, housekeeping. I'm going to be the one fielding your questions and handling the slides. So use that question box, use the chat box. If you guys have anything that you want to know, here is the time to pick these guys' brains. And you guys take it off from here.
Awesome. So Donna, you want to start and go give a quick introduction, and I'll go down through the first couple slides here.
Introduction of myself?
Yeah.
Sure. My name is Don McGriff. I am a mechanical engineer by degree. I've been doing polyethylene since 1993, and straight out of college. So it's the piping material that I know the best. I do a number of things for ISCO, including supporting the Snap-Tite group. I also do some technical assistance, and recently been heavily involved with our estimating group. So very happy to be here.
Awesome, thank you, Don. And Don McGriff's a good colleague of mine. I'm based out of the New England area. Both he and I regularly attend Transportation Research Bureau down in DC every year. Some of the stuff you guys will see today was actually presented in DC to a room of engineers. Today is mostly about efficiencies and creating inlet efficiencies, and some of these bullet points you see here right on this very first slide, for which I've animated, Cassie, so you might have a few clicks first before you get to the second actual slide. But so if you want to go ahead and start clicking through the animations here as I continue to talk. Really, what we're talking about, guys, is decreasing and alleviating headwater, right? And all in an effort to, when we talk about relining a pipe, usually with a segmental liner, be it high-density polyethylenes, such as Snap-Tite, or profile wall HDP, or metal pipe, or any other segmental liner, typically what we are doing is decreasing the waterway area because we're putting a pipe within a pipe most of the time. So, you know, your waterway area is getting smaller, but we want to alleviate headwater concerns. So what do? And the message here today is really about optimizing culvert hydraulics, starting to look at the inlet a little bit closer whenever we talk about slip liners and things of that nature. So these four things that Cassie's animated up for us here today, that's what today is all about. All right. So again, you know, for a long time, everyone thinks smoother is better. And that is true to a sense. Smooth pipe is good. You know, there's higher Manning's coefficient. So typically when we're talking high density polyethylenes or smooth wall pipe, you're down in the 0.009 to 0.012 range. And therefore you can often decrease the size of the pipe and still maintain similar flows. But it doesn't mean we should neglect the inlet geometry. So once again, as I mentioned in the previous slide, waterway area, where again, it's a pipe within a pipe. So you have to do at least, you know, most of the time you're 2 inches or 3 inches smaller, let's say when you're putting a Snap-Tite pipe inside of an existing corrugated metal. The pictures you see here are the two on the left. That's me standing there on the left before we put the HydroBells on and we slip line these. A sinkhole had actually happened on grade in this very nice neighborhood, only one way in and out, so emergency vehicles, they can't dig the road. We slipped the pipes, and because the sinkhole had developed, the hose pipe had actually already started to collapse. So we actually had quite a reduction in the waterway area. When you talk about a 36 existing pipe, we had to put a 26 liner in there, 26 OD, outside diameter pipe in there. So optimizing hydraulics became a question for the engineer and for the town. What do we do? So we opted to put the HydroBells, which you see in the center picture, which is a device that Don will talk about quite a bit here in a little bit, that optimizes the inlet efficiency of this culvert. So again, even though we've reduced the waterway area, we've actually improved the inlet geometry dramatically, such that the flows still check out when the engineer ran the headwater calculations to make sure they didn't flood the road. So a number of reasons why the HydroBell in that sense, help that project. And the one on the bottom right is actually from Western Massachusetts, where we actually slipped a old dilapidated rock box culvert that was falling apart and direct buried a brand new HydroBell, 54-inch. So some of these, you know, you guys, Kathy, I don't know if you've seen some of these in specs and documents and things of that nature. If you guys are opening up HY8 or HydroCAD or any other hydraulic modeling program, you may have seen some of these images in the past. And it talks specifically on inlet configurations. One of the worst conditions you can have for entrance loss is a projecting pipe. So just a pipe coming out of an embankment, right? The more we do to optimize those culvert hydraulics at the inlet, i.e. put a head wall and some wing walls there, is even better than just a pipe sticking out of embankment. And or beveling that inlet, which you'll see, Cass, if you want to move to the next slide. So the beveled inlet is the second one from the top, which is very commonly used. I know New York DOT uses it in their specifications, and a lot of other DOTs across the country actually write it right into their highway design manuals. So that right there is a very simple way to improve the entrance loss condition and keep your headwater elevations down. So you'll see a few examples of that shortly here. So here you go. Now, this doesn't come without some construction challenges, right? As you can see sort of in the picture there, that's one of my colleagues up here in the Northeast on a 96-inch pipe with an improved entrance. So they've got a poured head wall here, and what they basically did is they had to form up and create the beveled entrance. So time, money, but it is in fact a 0.2 entrance loss coefficient going into this pipe. So as the headwater, as water rises in a design storm event, it's actually helping with the fluid moving through that culvert versus it having to take a 90-degree turn or something like that with just a straight up head wall.
Don, I have a quick question for you, if you don't mind.
Absolutely. Never.
So one thing that comes up in engineering conversations, and I know that you'll be better answering this than I will, is if we do put one of these improved inlet devices or we do a beveled entrance to bring water in faster, how is that affecting our outlet? Because now water's moving out faster or more water's moving through, correct? So now what should we do on the outlet side to protect that side?
So good question. It's a dynamic situation, Cassie, right? So depending on if you're in low flow or medium flow and full flow, velocity is often governed by not just the entrance condition, but the actual area, right? So for those engineers on the call, you know that the simple equation, flow equals velocity times area. When we reduce that area, we're increasing velocity. So inherently, anytime we do a liner, regardless of the inlet, if that pipe's flowing full, we've increased the velocity. So the simple answer, Kathy, is add scour protection. Now, I'll tell you, I just came from looking at 4 pipes in Southern Connecticut yesterday, where every single pipe, the bottom was rotted out. It's nice, beautiful old New England stone-built head walls, but the bottoms are rotten. The head wall is blown apart at the bottom, and there's a scour hole the size of Texas at the outlet. So, you know, they've already got scour problems there from washout over the years of just a non-protected inlet or invert, excuse me, right? And stuff kind of just water moving around those outside edges, what we call piping, right? Water moving outside the pipe. So, you know, putting some stone in there, adding some riprap, trying to protect scour from happening in and around, not just the pipe, but if there's head walls and wing walls, those can be scoured out too. So you want to protect them.
Okay, I kind of knew that wouldn't be a simple answer, but I thought I should ask it.
Riprap. There you go. You know, I guess I'll just back up a step and say there are situations. I did one in Pennsylvania for the DOT last year that their velocities were so high, they had no choice. They had to line the culvert. They knew they were going to have some velocity issues. So what they ended up doing was designing a Contec scour protection pad at the downstream end of the culvert. So, you know, your Armor Flex, your heavy armor type products to protect the stream bed and the channel that you're actually exiting to from scouring out. So those velocities can be calculated and it can be protected.
Okay.
So You know, interestingly enough, and I don't know that a lot of folks on this call or we even consider it sometimes, I have to remind myself, with Snap-Tite, for those of you who are not familiar on this call with Snap-Tite, we'll talk about it. It's a solid wall, high density polyethylene with a male and a female end. The female end, as you can see in that little snippet I put on the top right there, is actually already beveled. So what that allows you for, as long as your bulkhead has a bevel to it, it allows you to maintain that little bevel action by having that female end out at the inlet side, right? So you're building into your female end, it all stays nice and beveled. But we're going to talk about the HydroBell. We talked about bevels already, category B there. Just simple addition of head walls and wing walls versus a projecting culvert. And some reducer stuff. I'll show you guys some pictures of some eccentric and concentric reducers that we've made out of high density polyethylene, which again, some of you folks on the call might not even be aware that we can make them. So the pictures will be good for you to see. So here you go. So specifically, there's some states here in the Northeast that absolutely love to utilize these. They're pretty commonplace for us now to draft them up, as you can see on the left-hand side there, and fabricate them. There's even provisions for when you cut these pipes, how do you finish them so they look nice and clean? And so what you're seeing here in this photo is actually in the CAD file, if you can read the diameter print there, you're looking at a 78-inch by 60-inch, so 78 big to 60-inch for the trunk line on that pipe. And you can tell, not only are we maximized, so what they've done is they've actually opened up the flow area at the inlet, right? So you have maximized waterway area, but they've also beveled the entrance. So keeping in that same kind of concept of keeping everything efficient at the inlet. So that's what you're seeing there. And then you see one with a cutoff wall built into it in the center photo. Center photo, it's all right. And then on the right-hand side, that's actually one we put in Southern New York. That's a profile wall HDPE to solid wall connection chassis. So I don't know if you had seen those before. We can make, like for example, that's a 72 by 63 inch. So it went into a 63-inch Snap-Tite reducer.
I've seen this done once. Yeah.
Okay, we can jump to the next slide. Just more examples. So once again, you can see kind of what they do is they take the circular pipe, they cut little sections out of it, and then they fold the sections remaining in and then weld the pipe back together. So what you end up with is a nice taper or a nice conical section that allows for the reducer to be created. And then it's hard to tell, but if you look at the picture on the right, we've plated the pipe up so it's a nice flush finish instead of the pipe ends being all exposed in open profile. So it's completely solid and built so it'll last for decades. I'm going to let Mr. McGriff take over from here.
So the focus of my portion of this presentation is really to redo some information that we presented at TRB last January, not of 2019. We had a three-pronged focus. One, just making people comfortable with the relining application of putting a pipe inside of a pipe, then specifically addressing the strength of that, which seems to be less and less these days. I think we've made people comfortable with the fact that we can put a plastic pipe inside of an existing liner, and if we have the right grout, and really those grouts don't have to be very strong. The sailor grouts that we are offering have enough strength in and of themselves, and the sailor has some advantages in the installation of being lightweight and flowing where you need it to flow, not leaving voids. But the last portion of our presentation was trying to get people comfortable with the fact that just because you reduce the area doesn't necessarily mean that you reduce flow. A Reline culvert is going to automatically reduce the diameter. And so if you think about this, as Don said, in a manning situation, and you compare a mannings of a 30-inch CMP versus a 24-inch smooth wall, they're going to be pretty close. And that matters from a capacity standpoint really in a low flow situation. But what we want to focus on is the fact that hydraulic demands typically are going to change beyond just the culvert itself. The water that's coming down through culverts typically always increases because of population growth, more paved roadways, just the amount of runoff that typically occurs these days as compared to some time in the past is going to be higher. And so there's going to be an increase in headwater, which we try to deal with. And then, you know, if headwater becomes too high, as Don said, you get roadway overtopping, and that's where, you know, safety issues come. Damage can occur. But we have to balance all of those things of, you know, smaller pipe and potential increase of headwater with just the overall economics. We have a number of culverts that are failing, and they all can't be dug up and replaced or increased. And so we try to make people comfortable with the fact that all things being equal, you can get a Snap-Tite liner in with a HydroBell and potentially not lose any flow. So Cassie, if you'd advance to the next slide. So we presented this example was actually one specific example that we have done, and this was a 72-inch corrugated pipe with a 0.24 Mannings. The entrance loss of this particular example was, well, we don't know. So we're going to look at a number of different possibilities, but we do know that we are relining with a 63-inch Snap-Tite with a Mannings of anywhere from 0.10 to 0.12 that's typically accepted by state. We know that its low is 0.009 and have data to prove that. And then that the entrance enhancement device, the HydroBell, has a entrance loss coefficient of 0.2. And then I typically confuse a lot of people, even hydraulic engineers, with the entrance loss or inlet control design coefficients that we list there that were laboratory derived. And what I've determined is that a large number of people who are designing are not using the inlet control equations that FHWA has used. I think it's in FHW5 that speaks to it. But most of the time we're talking about an entrance loss coefficient. The one thing that, to back up a little bit to follow up what Don says, is we know we can put a reducer on a pipe and it improves the flow. The difficulty we have with using that is that we can't quantify it as well as using a HydroBell. Now, I didn't put a picture of a HydroBell specifically, you know, and the animation that we have on the website, but, you know, it's designed to optimize the way the water gets in. We have a flat face panel to it that could be mounted up against the head wall. But what we're trying to do is keep water flowing in from 90 degrees into the pipe and do it with a rounded bell, hence the name. And one of the things that we also, Don and I, spend a lot of time is trying to get people to make sure that they're not putting that HydroBell out or projecting from the culvert. What we're trying to do is keep water from getting behind any inlet improvement device, because then you have to turn 180 degrees. You have to basically go from top of pipe all the way around the edge and into the pipe. So, but we can't quantify the HydroBell against a flat face wall, and especially compare it to what it would have been without a HydroBell, which is where we were about 5 to 10 years ago. Go ahead and advance, Cassie.
And if I may, while she's advancing that slide, Don, I want to pound on that specific point that you just stated. The deal with those reducers, the pictures you saw from New York, most of the time, I would say 75 to 80% of the time, it requires the inlet length to be increased. So they're extending I got to get my French hands going the right way here. They're extending the length of the culvert at the inlet, which is obviously bringing, with your slope, it's bringing your elevation higher. So it can, unless you model it, it can often actually be detrimental to the hydraulics to bring that inlet piece further out from the existing head wall. So those things have to be considered. The benefit of the HydroBell that Don's suggesting is that we're not extending the length of the culvert at the inlet. So thank you, Don.
Right.
So a question
Yeah,
for you
so-
guys that came in is, sorry to interrupt you, Don, is when would you use the HydroBell versus the reducer? Since you're saying that the HydroBell is flush and the reducer would bring it out, when would you use the two and why?
We typically prefer the HydroBell to be used in most situations. The issue is that we have a limitation on manufacturer with the HydroBell, so we only go up to the 63-inch size that matches the Snap-Tite. Typically going to work well with inserting into a female end of Snap-Tite. When we don't have that option, we're working with profile pipes that are bigger. Then we move to the other options, such as a reducer that is still available, but not as preferred as, say, the HydroBell. That's a good question, though. And I do want to say, I'm not going to get into too much of the HydroBell installation part of it, but, you know, it does have a flat plate, as I said. It is made from fiberglass. And people say, well, you know, why don't you use polyethylene like you do with the pipe? And we did early on, but the manufacturing costs are just pretty exorbitant to get the shape that we want, doing it in polyethylene and having the strength. And the fiberglass works well. It's flame resistant, works well for at the end of the culvert. You know, we've created marking lines for cutting, so you can cut the bottom off. So if you want the invert to sit flush, if you don't have say an entrance pool in front of it, we do have a flat face to mark to use as a form or to just mount against. We have boat hole pilot holes marked, and we have a marking line for the circle if you just need a circular shape and you want to get rid of the flat face. So back to the hydraulic example. So in working that example of 72-inch corrugated metal, we could figure out what a capacity could be based upon a number of assumptions. Headwater and tailwater depth play a role to whether something is an inlet or outlet control. As you can see in the next to last column, most of the times in the example we were running with these headwater and tailwater depths, we were inlet control, but one time we were in outlet control. And it is a complex issue. It's one that I wish I knew better. And I try to, you know, have discussions with hydraulic engineers to make sure I'm not speaking of ignorance because of just my level of understanding versus theirs. But when you are putting a smaller pipe in, you're typically going to force this pipe into inlet control, meaning they're only going to flow as much water as that inlet's going to allow. So the enhancement device, the HydroBell, is trying to improve that. But if we have an existing one to compare to, you can see with headwater depths being low, that your capacity could be 61 to 66 CFS, and if they're high, but it's not an outlet control, you can be up to 350 to 390. So when people say, well, what's my flow? There's a lot more than just the pipe that goes into it. It's the hydrology of what's feeding it and what's backing it up on the downside that could be forcing it an outlet control. But most of the time, when you're relining, you're going to force an inlet control condition. If you will, go ahead and advance. So one of the things that we determined with the laboratory testing, and this is what this graph represents, is what happens if I just reline it and I leave it essentially a plain flat end of polyethylene that's grouted with a head wall, but no bevel. Typical that what people would use or would leave 10 years ago, and it may still do now. So what this line shows you is the improvement as headwater increases. The HydroBell gets a flow rate that's improving at a better rate than the plain square end. Advance to the next slide. This is kind of saying the same thing, but what it's showing you is that as headwater increases over the diameter of the pipe, so it doesn't matter whether it's 12-inch or 60-inch, if your headwater depth as a ratio compared to the diameter, as it increases, as headwater goes up, this HydroBell gets more efficient. So you're going to funnel in early on when headwaters are just getting over the top and starting to rise, you're going to be in the 20 to 25% range. But as headwaters increase, then it's going to increase up to 35%. So the HydroBell actually is more efficient as you go higher. So when we run the calculations, and there's that square end that I'm talking about, even though it's with a wing wall, we're basically got a flat end front, versus if we put a HydroBell that's got a nice rounded bell shape into it, and also has a what we call a vena contracta. It's a little bit of a recess just beyond that inlet that kind of helps the eddies give a place to get out of the way, as the way we describe it. But in our flow rates here, a head wall or a HydroBell, again, we're dealing with the same headwater depths, tailwater depths. You know, we see a capacity of 50 to 60 on the low end, and then 280 to 380 on the higher headwater depths. So what this results in, Cassie, if you can go to the next slide, and this is kind of where I'd like to spend the remaining time. So the three lines that you see, the gray, the red, and the blue, those are the capacities that were available to the original corrugated metal pipe, assuming three of those different inlet conditions, with the gray being just a plain head wall, red being moderate to slope, and blue being a little projecting thin edge, and a projecting being the worst in most cases. Sometimes that miter actually ducks below it, as you see in the third bars. But you can see a range of where we might expect those flows for the corrugated metal. The bar charts, the yellow and the green, are essentially the polyethylene reliner. Green being, this is what it would be if we had done nothing. And on the low end, it's going to be pretty close, but as you start to increase the headwater depth, you can see that we are losing capacity compared to the original pipe. But if we put a HydroBell or some other inlet enhancement device, typically somewhere around entrance 0.2, then what we can do is get the flows back up to almost the maximum capacity. If you look at the 12-foot ratio, the headwater depth, we're better than two of the three inlet conditions that existed for the corrugated metal, and we are essentially equal to the square edge with a head wall that was existing before. So when people are trying to make this hydraulic decision and they're worried about a 63-inch pipe cutting down the diameter of a 72-inch corrugated metal by essentially 9 inches, or if you want to look at IDs, 12 inches, there's this concern that I am necking flow down so much that I'm not going to get the same capacity. And we're saying it's still possible that you get the same capacity, and don't let that be a factor in making a smart economic decision of relining with a plastic pipe, because your hydraulics may or may not suffer, and if they do, they may not be very much. I don't know that I had anything past this other than maybe, a couple conclusions. So we're saying that, with the right inlet device, you can, still maintain flows. One of the things that we argue against and we see is a lot of people prefer cured in place liners because they view that they're cutting the ID down less than they would with a plastic liner. And there's all sorts of other factors that go along with that, that we would argue against. Don, I'd let you kind of work on those conclusions as well as far as what you've seen.
Yeah, I mean, to the last bullet point, which Don kind of touched on, when other types of liners are utilized, typically there's no consideration for inlet modifications. So I would encourage folks, if they are considering a different type of inlet modification, or slip liner or liner solution, that they should look at the inlet, because again, it's about what Don and I just talked about is heavily related to the entrance of the pipe and keeping headwater conditions down. So, when we do consider a liner, and again, guys, don't hesitate to call Cassie or myself or Don when it comes to, hey, I got a candidate. I'm not even sure if it's a lining candidate. It's poorly failed. We've slip lined and salvaged culverts that have actually already failed. So, you know, it's worth the phone call no matter what condition the pipe's in. We might tell you it's time to dig that sucker up and replace it, but it does not hurt you guys at all to call us and reach out.
Yeah, thank you guys so much. We almost hit it on the nose this time, which is a first for us, Don.
Yeah.
Yeah. If you guys have any questions, I'm going to hang on here for just a few minutes and we can answer any of those. Otherwise, feel free to jump off. We'll just hang out and see if you guys have anything that you would like us to answer. We do have Reline Live again next Thursday, same time. We'll be talking about grout injecting to stop infiltration before slip lining. I don't know if you're joining us for that one, Dawn, or not, but you introduced me to Chris, who is going to be helping host. Yeah.
Yeah, I may be on that. Absolutely. That's
okay.
it.
So that Dawn knows a little bit about this product, Avanti, that we'll be talking about. So he introduced me to this product. It'll be really cool because I haven't really had a chance to dive into that one yet. So yeah. Okay, I don't see any questions coming in. You guys have a wonderful rest of your week. Thanks for joining Reline Live. Feel free to hit up Dawn and I if you need anything. Otherwise, I will put a copy of the presentation in the thank you email that goes out tomorrow.
Thank you, Cassie. Appreciate you doing this.
Thank you, guys. Thank you, Dawns. I love it, the Dawns. We're going to have you back.
See you guys.
Thanks, Cassie.
See you guys.
See you guys.